Dear students, നമ്മൾ ഇന്ന് ബെസ്റ്റ് അപ്രോക്സിമേഷൻ എന്നുള്ള പാർട്ട് സ്റ്റാർട്ട് ചെയ്യണം. അപ്പം പുതിയൊരു സെക്ഷനാണ് നമ്മൾ സ്റ്റാർട്ട് ചെയ്യുന്നത്, ബെസ്റ്റ് അപ്രോക്സിമേഷൻ. ആദ്യം നമ്മൾ സ്റ്റാർട്ട് ചെയ്യുന്നത് ഡെഫിനിഷൻ വെച്ചാണ്. ഫസ്റ്റ് ഡെഫിനിഷൻ, അറ്റ് എക്സ് ബി ആൻ ഇന്നർ പ്രോഡക്റ്റ് സ്പേസ് ആൻഡ് ഇ ബി എ സബ്സെറ്റ് ഓഫ് എക്സ്. എക്സ് ഈസ് an element of x. Then the another element what you are taking, y of e is said to be a best approximation from e to x if and only if norm of x minus y less than or equal to norm of x minus z for all z in e. As you know, this y is called the optimum solution for the following problem. In that way also we can discuss as a problem, solution for a problem. What is the problem? Minimize norm of x minus z subject to certain e. Here x minus y is called the optimal error, and norm of x minus y, that is nothing but a distance between x or distance of x from e. Actually, what is that? Infimum of norm of x minus z such that z is an element of e. This is for the best approximation definition. Coming to the first theorem, let x be an inner product space. There is statement. There are three parts. Part A, at E subset x and x element of e bar, and the x is a best approximation from e to x if and only if x is an element of e. And part B is if e subset x is convex, then the x is at most one best approximation from e to any x in x. And part C is f be a subspace of x and x element of x, then y element of f is a best approximation from f to x if and only if x minus y is orthogonal to f. And in that case, distance x from f, that is defined as inner product x minus y. We can come to the proof of it. As usual, it is given x is an inner product space, and part A, we are coming to part A, that E subset of x and x element of e bar, taking an element small x in e. What is norm of x minus x? As usual, it is 0, which is less than or equal to norm of x minus z for any z in e. And clearly, x itself is the best approximation from e to x. So first part, or one part at least we have proved. Now suppose that y in e is a best approximation from e to x. By definition, norm of x minus y less than or equal to norm of x minus z for all z in e. That is what we have written earlier. You can call it as equation star. We have x an element of e bar. What does it mean? There is a sequence. Yes, sequence xn and e such that xn converges to x in x as n tends to infinity. So using norms, we can write norm xn minus x is tending to 0. Or same way, norm xn minus x is same as norm of x minus xn, which is approaching 0 as n tends to infinity for xn in e and n in n. That is for all n in n. And by star, that is the equation given above, norm of x minus y less than or equal to norm of x minus xn for all n in n. What is the reason? Xn is an element of e for all n in n. And the above equation what you have written. So norm of x minus y is, see what you are getting in norm of x minus y less than or equal to norm of x minus xn. And of course, xn converges to x, or norm of x minus xn tending to 0 means this tends to 0 as n tends to infinity. Or we are getting norm of x minus y equal to 0, which implies x equal to y. This implies x is an element of V. Why? Because we already taken y is an element of V. That is what the first part, proof of the part A. Now coming to the proof of part B. What is given in the statement? E is convex. Of course, E subset X, which is a convex set. Taking an element X in X. If possible, assume there are two best approximations. You want to prove y1 equal to y2, or you are taking two different approximations and showing that it is unique, or you claim that y1 equal to y2, as y1 and y2 are the best approximations. Take d as distance of x from E. D equal to distance xe. By definition, norm of x minus y1. Because both it is true for both y1 and y2, means is equal to norm of x minus y2. Call it as equation 1. Because y1 and y2 are the best approximations from E to x. So both y1 and y2 are elements of E, means y1 by 2 plus y2 by 2. That is y1 plus y2 by 2 is again an element of E, because E is a convex set. So we get d less than or equal norm of x minus, earlier you are written y1 or y2. Instead of that, you are replacing by y1 plus y2 by 2. You call it as equation 2. By using parallelogram law, we have is 2 times norm of x minus y1 square plus 2 times norm of x minus y2 square is equal to norm of 2x minus y1 plus y2 square plus norm of y2 minus y1 square. Because x minus y1 is an element of x. X minus y2 is again an element of x. And we are using the parallelogram law. So ultimately we get norm of y2 minus y1 square is equal to 2 times norm of x minus y1 square plus 2 times norm of x minus y2 square minus norm of 2x minus y1 plus y2 square. And in each case you see less than or equal to norm of x minus y1. Norm of x minus y1 is taken as d. Norm of x minus y2 is taken as d. So 2d square plus 2d square. Other one again d. 2x minus y1 plus y2 square. By from equation 2 we are getting d is less than or equal to norm of x minus y1 plus y2 by 2. So ultimately this is again less than or equal to 2d square, or 2d square plus 2d square minus 2d square. 4d square minus 4d square is equal to 0. That is norm of y2 minus y1 square equal to 0, or y1 implies, or y1 is equal to y2, because norm of y2 minus y1 is 0. That is uniqueness part is proved. Part C. What is part C? Let f be a subspace x, and x is an element x. As an element x is taken, take one more element y in f in such a way that x minus y is orthogonal to f. What we have to prove? We have to prove that y is the best approximation from f to x. Instead of E, we have taken here f as the subspace x. So we have to prove that norm of x minus y less than or equal to norm of x minus z for all x in f. For that, y an element of f, z an element of f, or y minus z is an element of f. It is true because f is a subspace of x. What does it mean? Yes, by the earlier result, norm of x minus y is orthogonal to f. So what I can write? X minus y is orthogonal to y minus z for all z in f. Again we are using our Pythagoras theorem. Norm of x minus z square is same as norm of x minus y square plus norm of y minus z square, which is definitely greater than or equal to norm of x minus y square for all z in f. What is the reason? X minus y plus y minus z is same as x minus y. That is, we can split it and write in that way. For norm x minus y is less than or equal norm x minus z for all z in f. What does it mean? Y is a best approximation from f to x. On the other hand, converse part we have to prove. Take the other side. That is conversely. Suppose that y in f is a best approximation from f to x. What do we have to prove? We have to prove that x minus y is orthogonal to f. Take z in f with the unit norm. Norm z equal to 1. Take w. Instead of w, take omega. Omega is better. Omega equal to y plus norm of x minus y x into z is an element of f. Reason is f is a subspace x and both y and z are elements of f. And we know y is a best approximation from f to x. So what you can write? Norm of x minus y less than or equal to norm of x minus omega for all omega in f. Now consider norm of x minus y square. Just rewriting. This is less than or equal to norm of x minus omega square. What is that? Inner product x minus omega, an expansion. Inner product x minus omega is replaced by y plus inner product x minus y z, both sides, is equal to expansion x minus y. Just expand it. That is the inside the inner product. You expand it and write x minus y. Then you are getting x minus y z is taken out. X minus y, then x minus y z, x minus y, just rewriting x minus y, then minus, that is first part, minus is multiplied outside, that minus is replaced. In the second term, what is done? X minus y, again minus is multiplied, inner product x minus y z. Now expanding with the inner product wise. So x minus y first term, other side x minus y first term. So x minus y. Then what about that? X minus y. Second term, what is that? What about the second term? X minus y z is taken out. So it comes with a bar. Inner product x ky. What is that? K bar inner product xy. So in the same way, x minus y z bar x minus y z. And second term was minus inner product x minus y z x minus y. Again second term expansion x minus y z x minus y z bar inner product is z square. That is norm z square. So norm of x minus y square minus modulus of z in z bar is mod z square. X minus y z square minus x minus y z square once again, and plus is norm z square is 1. So modulus inner product x minus y z square is equal to norm of x minus y square minus 1 term cancelled modulus of inner product x minus y z square. So we are getting ultimately norm of x minus y square, which is on the left hand side, which is less than or equal to norm of x minus y square minus modulus of inner product x minus y z square. So on comparing both sides, you see like terms cancelled. Ultimately you get the second term is nothing but 0. So norm modulus of inner product x minus y z square is 0, or inner product x minus y z is 0, or x minus y is orthogonal to z for all z in f with the norm z equal to 1. Now z is arbitrary. Z in f is arbitrary. So if z equals 0, inner product x minus y z equals 0, which implies x minus y is orthogonal to z. Suppose z is not equal to 0, that is norm z not equal to 0. So you can define a new term z dash, that is nothing but z divided by norm z. Definitely is an element of f because f is a subspace x and norm of z dash is 1. Using one result, our star we are getting x minus y is orthogonal to z dash. Or inner product x minus y z dash is 0. Replace z dash by z by norm z. 1 by norm z taken outside. 1 by norm z into inner product x minus y z equal to 0. Or norm z is not equal to 0. Of course, what are you getting? Inner product x minus y z equal to 0. Or x minus y is orthogonal to z for all z in f. Now suppose that y in f is the best approximation from f to x. Then we have a distance formula. Distance x f square. We had written that distance earlier. That is now my x minus y square, which is inner product x minus y and expansion x minus y minus y x minus y, or x minus y is orthogonal to f. So that inner product y x minus y is 0. Second term is 0. We are getting inner product x minus y. Our distance xf is, it's a square, right hand side, it's a square root. That is inner product x minus y. It's the square root means raised to half. Our distance xf is equal to inner product x minus y raised to half. That's all about the first theorem. We conclude it here.